The title of this note is Implicit Differentiation. Make sure you have your name, date, and period in the top right-hand corner. And your outcome is to derive any implicit equation. So we're going to start by defining what that means. Up until now, we've mostly dealt with what are called explicit equations. An explicit equation is when y is explicitly defined. So y equals anything, or a quadratic, or a trig function. All of these are explicitly defined. An implicit equation is where we don't have y equals. We might have x and y combined on the same side. So an example might be x squared plus y squared equals 5. This is an implicit equation because it's not written as y equals. So how do you derive something that is not written as y equals? I'm going to put up the steps, and then we're going to do an example. So implicit differentiation, the first thing you're going to do is you're going to differentiate both sides of the equation with respect to x. In this chapter, it's always going to be with respect to x. It could be with respect to another variable, and we'll talk about that in a future chapter. Differentiating with respect to x means that you're doing dy with respect to x, means that dx goes in the denominator. After you've done your implicit differentiation, you're going to collect all your terms with dy dx onto one side of the equation. So you're just doing some algebra, add, subtract, multiply, divide, do what you need to do to collect dy dx. Do algebra. All right, and then again, you're going to factor out your dy dx so that there's only one of them. And then lastly, you're going to solve for it because that is the derivative. That's what y prime is, dy dx. Those two notations mean the same thing. So let's look at an example. Right, find the equation of the line tangent to the ellipse, x squared minus xy plus y squared equals 7 at the point -1, 2. So here's a great example of an implicit equation. We couldn't even solve for y if we wanted to because there's a y squared and a y. It would actually be possible, but it would take so long to do the algebra, it's not worth it. It'll be a lot faster if we derive it implicitly. Note it says find the equation of a tangent line. So when we're talking about equations of lines, we need a point and a slope. So that we can put it into point-slope form. Remember, that's y minus y1 equals m times x minus x1. The good news is we already have our point. It's right here, -1, 2. So that's x1 and y1. So what we're still missing is our slope. And so that's why we need to find a derivative. So to implicitly derive this, we're just going to go term by term and derive each term. So we're starting with x squared. What is the derivative of x squared? It is 2x minus xy. Okay, that's multiplication, so I will have to stop here and use my product rule. So I'm going to call that u and that v. So u prime, the derivative of x is the number 1. V prime, the derivative of y is y prime. We're going to use this notation dy dx. So using my product rule, the second term is uv prime plus vu prime, y times 1. I'm subtracting that entire term. Okay, then I'm going to keep going. My next term is y squared. All right, so the derivative of y squared is 2y. But I have to chain rule this. I also have to take the derivative of the inside function, which is y. So it's actually 2y times dy dx equals, and the last term 7, the derivative of a single number is 0. I want to stop for a minute and talk about the first term and the third term that I have in green and blue. They're actually really similar. The derivative of x squared, I could chain rule this. It's 2x times the derivative of x, which is dx dx, because I'm deriving with respect to x. With respect to means it goes in the denominator. And dx dx is just 1. So 2x times 1 is just 2x. That's why that term is just 2x. But then when I do the exact same thing with a y in it, it's 2y. The derivative of the outside function is something squared, so 2 times the inside function times the derivative of the inside function, still with respect to x. That time it's not 1, which is why this blue term is just a little bit different. All right, so now what I want to do is I want to collect my dy dx terms. Sorry, I'm trying to move all this stuff out of the way. Okay, so notice that this red term, I have subtraction. I'm subtracting everything here, so I'd like to simplify this a little bit. So I have 2x, and then I'm going to be subtracting everything. So minus x dy dx minus, and I'm going to simplify that, y times 1 is y, plus 2y dy dx equals 0. All right, so I'm going to collect all of my dy dx terms on one side of the equation. So here's a dy dx term, and here's a dy dx term. So I'm going to elect to leave those terms there. So I'm going to move my 2x to the other side of the equal sign. And I'm also going to move my minus y to the other side of the equal sign. So that will leave me with negative x dy dx plus 2y dy dx on the right side. And the left side will be negative 2x plus y. All right, so that was the second step, to collect your dy dx. Now, every term on the left side has a dy dx in it, so that's our GCF. So I'm going to factor out the dy dx. And then the very last step is to solve for dy dx. So to get dy dx by itself, I'm going to divide by this factor. So dy dx, which is the derivative of y, is all of this stuff. And I'm not going to try to simplify it any further. I'm going to leave x's and y's in my answer. So that's it. That is the derivative. Now we remember we wanted to find the derivative at the point -1, 2. So -1 is the x value, and 2 is the y value. So we can actually go ahead and just substitute those two values in for x and y. So the derivative at that point, and the notation for this, when we're talking about the derivative at a certain point, we're going to draw a line, and in the bottom right-hand corner, we're going to write the point that we're talking about. So we're saying the derivative at -1, 2 is, and we're going to go ahead and substitute in our x and our y values wherever appropriate. And then I'm just simplifying here, doing this arithmetic. So this is 2 plus 2 is 4. This is 1 plus, sorry, this y value here should be 2. 1 plus 4, so it's 5. So the derivative is 4/5. So going back to my original question, what's the equation? I'm going to use my point slope form of a line that I have right here. And let's see if I can pull this down. And I now have all of the pieces. So for my equation, I will have y minus y1, which remember is 2, equals the slope that I just figured out, x minus the x coordinate. And then I'm going to simplify here. and that is the equation of the tangent line. That's it for our notes. Go ahead and draw your line for your summary and bring your notes into class.